Welcome to Automotive World, everybody. Thanks for joining us. I'm delighted to welcome you to today's webinar, which is on the subject of automotive safety-critical multi-core ECUs. Today we're going to hear from Roman Iseler and Joachim Hampp, who will discuss development cycles and how they can be accelerated for safety-critical multi-core projects. What's behind this? Well, there's a growing number of electronic control units in new vehicles, bringing in ever more functions. Advanced multi-core ECUs, electronic control units, have been developed to process multiple functions simultaneously, but growing safety requirements are increasing the overall complexity of such projects. Altium, which works with leading Tier 1 suppliers and automakers, has developed the tasking safety checker. This can be combined with Elektrobit's AutoZar basic software EB Trezos AutoCore to help establish a smoother and faster workflow. So over the next hour, we're going to hear from Roman Iseler, who is Product Manager at EB, and Joachim Hampp, who is Global Product Architect at Altium. And they're going to explain in greater detail about this and introduce components that are involved. As ever, we'll make slides and a recording of the event available afterwards. We'll send you an email to let you know how and when you can access those. And we'll have a Q&A session as well following the presentation. So if you would like to ask a question, please feel free to type it into the Q&A box on your screen. Type your question in there and we'll address as many relevant questions as possible in the time that we have available. That's all from me. Now I'm going to hand over to Roman and Joachim for how to handle growing complexity in automotive safety-critical multi-core ECUs. The floor is yours.
Thank you, Martin, for the introduction. Let's get started and have a look at the agenda for today. So first of all, we will have a quick look on the motivation behind safety, and also look at use cases and scenarios where safety is a big issue and how to improve basically these use cases. Then Joachim will talk about the tasking safety checker tool, the functional overview and how it works. And at the end, we will have a quick look out on how to integrate that into your project with EB Trezos in an AutoZar environment. So let's get started. On the motivation, so we have usually with safety, we have three challenges when it comes to freedom from interference. So the first one is the spatial domain, where we have freedom from interference on memory integrity. So it means we have no unintended writing to memory of other partitions or software parts which should be separated from each other. Then the second one is the freedom from interference on the timing and execution domains, or the temporal domain. Here the goal is to guarantee an execution, a smooth execution, and also prevent a wrong allocation of processor execution time during the runtime of your software. And then the last one, the data domain. Here we talk about freedom from interference on communication, so loss of communication or changes in the data which is communicated on the bus. For today, basically in the domain of safety, we want to spend a little time within the spatial. And here, so for freedom from interference on memory integrity, we would look at three use cases, or four use cases, actually five. We have one is software architecture, definition, and design. We will have a quick look at disturbance-free application for lower ASIL levels. So particularly we talk about usually ASIL A and ASIL B. Then for integration support in systems with memory partitioning, where we have the usage of an MPU, a memory protection unit. So this is something we usually see in the higher ASILs, C and D. And then we have two use cases which are fairly similar: the reuse of legacy code. So you have application component which was used in a previous project and gets now ported to the new project, or a third-party module integration. So basically, if you have in your ECU project the need to integrate software components which are not known to your organization, and you don't have the full control over the functional behavior. So let's get started with the first one. This is actually something to get started as early as possible. This is the recommendation anyways for every safety project, to think about your architecture and your requirements first before you start putting together the architecture and safety concepts afterwards. So what would be the benefit of having support here? So the problem usually is early validation, and with this the tooling support we will show you today, you will have the possibility to identify issues early in the process. So if you have communication between modules which is unknown, and you get some early guidance to follow then later in your safety strategy. So this helps you to get started as early as possible in your process, as high up on the left side of the V as possible. Now, if we look at the use case for the disturbance-free application, so actually the scenario could be as follows, right? So you have a normal integration with basic software, so your system is already all set on AutoSAR components, and you now have the need to implement or integrate a safety requirement which is mapped on this application. So the challenge is to integrate this and have a mixed criticality system. Means you have normal function code and your safety function code coexist side by side in your application. So if you are in a situation where you have the limitations either due to hardware limitations, one could be the availability of a memory protection unit. So means your hardware does not provide an MPU, and other mechanisms like double inverted storage of data to achieve a protected memory is too resource costly in terms of execution time and or memory. Here you would have the challenge that your safety application, your normal functional applications or non-safety application coexist together with BSW, MCALs, RTE, all in the same domain or context. So the solution on this one would be to achieve a freedom from interference argumentation, so that all of your software components or software parts coexist within the same memory context, so you don't have a separation of any kind. Here, the argumentation could be based on a quality process argumentation, so what we call at EB a non-interference argumentation. So we guarantee that all other software parts which do not fulfill safety requirements do not interfere with the safety application, so do not write into that memory space. In combination with the safety checker, that actually would also add a technical argumentation to this point that there is a proof that none of the other application parts write into this safety application component. So with this, we'll move on to the next use case, which is actually a system where we have a usage of memory partitioning. So we use the memory protection unit, for example, and a scenario would be as it's shown in the picture. So we actually do have also coexistence of a safety application, so a safety application which fulfills the safety requirement, and functional applications which fulfill normal functional requirements, and they are separated through a memory separation, memory protection mechanism into smaller partitions. The system works like this, that usually the operating system or some other mechanism will separate your memory into small partitions which are protected from each other, and there are mechanisms in place which enable you to communicate over the partition borders. Now, the point is that so in this case, the OS or some other part takes over the context switching and guarantees freedom from interference on the spatial domain in memory. Now, to prove your system right, so you need to basically design maybe also test cases which are not a real use case driven approach. So you would have special test cases designed, an extra debugging effort to see if your configuration for your memory protection is set up correctly. With the use of the safety checker, we would have an easier way, faster feedback, if you want, early in the process. So basically you could run, or you will run, the safety checker after compile time or during compile time, and you will get an immediate result based on your configuration, and you would identify possible problems within your partitioning setup early in the process without even the need for hardware in the end to flash and debug your memory protection violations. So here the advantage is clearly a faster development process. And if we look at the fourth and actually fifth use case, so they are pretty similar with the reuse of legacy code and the integration of third-party delivery. There we have actually software which is behaving in a way which cannot be influenced. So maybe I don't know the behavior in total, I just know the content or the interfaces to the outside world. And with the safety checker, I could basically also check correct behavior and have a second level of checking if the software behaves as intended, and I can also avoid unexpected access to memory, actually in both cases, so I can analyze my data flow for both scenarios. In the case of a third-party module, I could use it or I can treat it as a black box and just concentrate on the outside interfaces and protect the rest of my software where it is integrated. Okay, so now I would like to hand over to Joachim to give you an overview of the internal behavior of the safety checker.
Good. Thanks, Roman. Good morning, good afternoon, hello to everybody. Let's start at one point of a time. Everybody from you will have the challenge to go from a multi-core to from a single core to a multi-core. And in the way he goes from a single core to a multi-core could be different, but for sure there will be a lot of software components that will be reused and needs to be, let's say, mapped on a multi-core. Or on mapping all these components, there's for sure a software architect and a safety architect in place who distinguish what part of the software component will run on which core. But for sure you will have the scenario like it is here on the right hand side, that you have, let's say, software components that interact with each other. They exchange data, they exchange information, and because of the nature that you reuse a lot of software, or the safety structure is not 100% clear, or because of the pressure of the project, there will be parts of the code where the access goes direct, may not use the RTE or any kind of an inter-processor, inter-task communication mechanism to exchange data, to read data, to access data, to execute functions. Yeah. So because of that, it needs to make sure that the data which is exchanged does not hurt the application that has a higher ASIL level, yeah? Crash it or block it or stop it. This scenario is also the same if you turn on the MPU, but with the MPU turned on, you have the MPU in between, and this will for sure cause a trap or an exception if such an access takes place, and block the access. Okay. The result would be a change of the timing behavior. And as you come from a single core system and you have put all these components on different cores and you added new applications and so on, this can also change the timing behavior dramatically, as you don't know when these accesses to an, let's say, higher level ASIL application, these unexpected or not documented or not known, take place. Yeah. If you recognize these accesses during development time, then you can work against and fix it. But to highlight or to see these unexpected accesses during development time, you need either do a code review or you have to have the right tests in place. If you uncover these unwanted accesses or not allowed accesses in the field, then it might cause trouble in the product for not known behavior. Now, this shows the ideal world. On the left-hand side, you have several cores, core 1, core 2, core 3. You have different applications with different ASIL levels, and they just store, read, and write and access data which is assigned to them and separated in a separated RAM. So an ASIL A will not touch an ASIL D or ASIL B memory location, and everything looks quite fine. But with the ISO 26262, you have this so-called freedom from interference. That means it is also allowed that an application with an ASIL A can read data from an ASIL B or a higher ASIL level. Yeah. This is not forbidden, but to allow this, you need to have the right mechanisms in place on the higher ASIL level applications to make sure if there's something wrong written into this memory location, that the application will not fail. That means you have to put the proper tests in the application around so that this will not take place. The ideal, before was the ideal world, but in reality it looks like more like this, as also described before. As you reuse software, as you get software from third parties, as you get software from external deliveries, not everybody might be aware of the safety concept. Someone just is under pressure and reads or writes data to a location where he thinks it's suitable, and then you end up in a scenario like this, where a lower ASIL application reads or writes to a higher ASIL application. And the outcome, or what could be the issue afterwards, is not yet clear, except you have the right tests in place. Also with an MPU in place, this is protected, but then, as said, the memory behavior of your system changes. Or what also happens very often in development cycles is that the MPU is turned on to a very late stage, because you don't want to have the timing penalty that MPU puts in, or you want to have a fast moving forward in the feature implementation in your system that you develop, and for that reason you turn the MPU on late, and then you will get a lot of exceptions and traps if you have the right tests in place. And at that time, then you have all to fix all these traps. But the problem is you might not have all tests in place to find out all unwanted accesses that you want to protect. And this is then later found out in the field, for example. The safety checker is a tool that starts on your source code. And we now go from, let's say, from left to right in the picture. So you define in a configuration the safety classes. You can say, okay, you have an ASIL A, you have an ASIL B, an ASIL D, and you define, for example, also the access rights. That means all ASIL A are allowed to read from ASIL B, or access or write to ASIL B, and also vice versa. ASIL D is allowed to read and write into ASIL A, for example. And you can also specify with finer granularity. You can also say function XYZ can read and write or access the other ASIL class, and so on. Then you see in the right, middle right, you see these so-called validation data archives, the VD files. So any third party who does not want to send to you the source code, but delivers to you just the object files, can use the same tool and run it for his part. And out of that, the tool generates these VD archives, and you can, let's say, link in the VD archives into the safety checker. Then the access rights are also checked for correctness for the third-party deliveries based on their safety checker output. And it will be taken into the account as well if there's any kind of a violation. At the end, the safety checker will send out a report, and that's one we will see later. But just saying again, the safety checker is processor independent. It runs on your source code and is not dependent on any CPU or yeah. Okay. So as said before, what needs to be done? The safety class access rights needs to be defined. The functions and variables need to be defined, let's say, or the allocation of the functions and variables to their required safety classes needs to be defined. And when the tool runs, it gives a report, it prints a report, the safety checker report, so that you can verify what you've set up in the configuration is correct. And here we see, for example, that an Iseler, if you go down on the bottom left side, you see source, the Iseler has RWX, read, write, and execute on Iseler, but it's not allowed to do anything on Iseler B or an Iseler C, while an Iseler C is allowed to read, write, and execute on an Iseler B and just write to an Iseler. That's how it was defined by the safety architect via setting up the safety structure for the system. Then on the right-hand side, you have the safety class selections. And here you see, for example, a file underline .c. The name pattern, there you can specify in a finer granularity. You could put in, say, okay, function ABC, yeah, belongs to the class Iseler C. And if you've done all this and you run through, it could happen that there's some violation as printed here in the graph. So it will give you a call graph and will give you a similar output to a compiler output where it says warnings and errors. And here, for example, you have a check access for reading my struct Iseler from function F3 Iseler C, which was an access violation. But we will see another example here from Roman later on. And you can use this output to further processing or to fix the issues so that the safety architecture as done by the safety architect is proper in place within your system. You can run the safety checker as like a compiler, so you can put it as a kind of a pre-run tool in front of the compilers. That means you can put it into your build process, either if you do, let's say, engineering builds, or if you have build systems, you can put it in front and run it every time to check if the safety architecture is kept and verify against. Okay, for that I want to hand over back to Roman. Thanks.
Okay. Yeah, thank you, Joachim. So now, since we all know how the safety checker works, the big question is how to configure the safety checker. So we just learned that we need to tell the tool somehow where and how to access between partitions happen. So now a good question is, where is this coming from and what it is based on? And if we look at the AUTOSAR configuration, we actually would have 3 portions in our AUTOSAR configuration, which contain already the information we need to configure the safety checker. So the first one, all the way to the left, would be our OS applications. So here we already built logical units which we want to protect from each other, and also in the multi-core case assigned to a certain core. So that's what we see in the screenshot to the left. In the middle, the RT event mapping. This gives us the information on which runnable. So if we have a software component and an active component which is executed based on an event or on timing, it gets mapped on tasks through the event mapping. So through this configuration set, we know who's executing what, and also which context it is executed in. And then the third one, all the way to the right, is the RTE partitioning configuration. So here we already have the mapping of the components to the OS applications, and also with that the safety mapping within the whole system. So if we now convert that to the configuration of the safety checker. So Joachim mentioned the access rights configuration and also the selection. So the selection of source code or functional code mapped to certain access rights. There's one more parameter which needs to be configured, is the safety class attributes. So this one is something you could also set up within EBTracer Studio. So you have all of it in one tool. So you have your basic software set up in Tracer Studio, and you can also have a graphical interface to configure the safety checker in here. And yeah, in the future we're thinking about to link all that together, so we have a consistent system in here to get the whole system consistent and checked against each other. Now, this first parameter I want to talk about is the safety class attribute. Here it is more or less a mapping to the OS application. It is more of a logical abstraction to cluster your system to the different Iseler levels or QM level, and represent the different partitions. With the next parameter, we are talking about the access rights. So this is what Joachim already mentioned. We see also the report or the outcome of that in the report which is generated. Here we would define the access rights between our logical units with the safety classes. So if there's a read, write, or execution rights between the safety classes. And the third one would be the safety class selection. So in this case, we are talking about the real mapping. So which component is part of which safety class, and with this information, similar like a linker file, the safety checker knows how to check the different components against each other. So that would represent the configuration within the GUI. This can be automatically generated, and then the integration of the safety checker, as Joachim also mentioned, is fairly simple. So it is basically possible to integrate the safety checker to its similarity to a compiler in the same way as you would do your compiler. And then actually it doesn't matter if you have what type of compiler you would use. You would actually you could reuse also components here. So compiler calls for the inclusion structures, or also the file lists you're handing over to the compiler. So in this example, what we did is we integrated the safety checker into the build environment we deliver with our product, EBTracers, and created a new make target, in this case we called it safety check. So we type in make safety check, what you can see in the lower right corner in the picture. And then the process of the safety checker would start. It takes in the configuration, it pulls in all the necessary files and include passes, and goes through the process of checking the access between the different components. And it generates an output file, which we saw also as an example within the presentation from Joachim. And here I prepared a small example fitting to the configuration part we just showed in the screenshots above. And so this report actually describes the whole output. So we will have a file to partition mapping. So I did not put in a screenshot here, so we know exactly, or we could look how the configuration was interpreted. So each file is mapped to a safety class. We can see the safety class access right table, where we see also the metrics of accessing the different other application parts or safety classes we defined. And then on the lower end we see a call graph or the data graph, where we have marked all the access violations, so it can be easily found, can be also interpreted in an automatic way. So the integration into a CI system is also not a problem to get results with a nightly build or whatever cadence you schedule your continuous integration system. So in that call graph, you of course also see positive accesses. So I just pointed out here one problem we see. So I put in an access violation where in the function calls function is the IO hardware abstraction set discrete value, which is part of the OS application 1. So this is my safety class in this one, in this case, is accessing a component which is part of the OS application 0. So this is pointed out. So there is also an error output which can be reviewed, which is also helpful for the reviewing process. So I put in a small example here as well. So they are marked as warning information or with an E as an error. In this case, we have a closer look on the error, where we have the software component IO hardware abstraction.c in line 51. We can see that the call of DIO write channel which is part of application 0, is coming from the software component IO hardware abstraction set discrete value, which is part of another safety class. So the code I put in as an example. This would be admittedly a really simple example of an access violation, but this could also find more complex points and would be able to point out multiple locations, and you could basically identify them with the reported errors. Also, a short word on warnings and the information. So you could also go through then all your warnings and have a manual inspection of those to be sure of the completeness to your argumentation in terms of safety if it comes to free-form interference. Okay, and that already brings us to the end. So we have a short summary here. So what we've learned, right, the tasking safety checker is actually easy to be integrated into an AutoSAR project. It can be treated from a configuration standpoint, similar as your AutoSAR configuration, and also integrated easy into any built environment you use, or also a continuous integration system. The safety checker helps identify memory violations early in the process. So here, right, you can parse or static analyze your C code based really on the C files. So it's 100% hardware independent. We mentioned here as well the MISRA C 2012 standard. The safety checker provides information for manual inspections. What I just mentioned, you get also warnings and information out of the report for the completeness of your analysis. Since it is based on C code, it's not possible to have all combinations checked within the system. And then the safety checker also, and this is in my opinion the biggest argument, accelerates the integration process into your safety application project due to the fact that you get easy and fast feedback based on the fact that it is like your compiler. It's right after the generation time. So this can be used on every developer's desk, basically. Okay, and then the conclusion. So within the embedded community, benefits from synchronized tools. So we will try to improve our environment as much as possible, also going forward. And here, yeah, we create new values in cooperation between different tools. All right, and then I will hand over back to Martin.
Thanks very much, Roman and Joachim, for sharing your insight with us today. As ever, the slides will be available to download after this event, and we'll send you an email to let you know how you can access those. But we do have our panelists for another 15 minutes or so. If you'd like to ask them a question, please type it into the Q&A box on your screen, and I'll put those questions to them now. So let's get underway. Does the development environment have any influence on function?
So I take that one. No, it does not. So the development environment is independent. So the tool itself is standalone and has its normal license checks, basically similar as, or actually exactly the same way as a compiler would work. And if it's possible to integrate different compilers into your development environment, the tool can be integrated fairly easy and straightforward. On the function of the target code, it does not. It is basically a static code analysis and will just report or generate the report. And what happens then with the report is up to the user, basically, but it doesn't have any influence on the output.
All right, thank you. What tool confidence does the safety checker provide? What level of tool confidence?
I take this, Joachim. So we developed the safety checker according to ASPICE level 2. So that we can assure that it is usable for up to ASIL B. We have not yet went into a qualification with the tool. That's maybe for future plans. to also to take the tool into the tool qualification.
Great, thank you. Can you provide, are you able to provide any success stories that have already occurred as a result of customers using this setup? Perhaps you can, if you're concerned about confidentiality, perhaps you can frame it within the context as opposed to naming a company's name.
So so what we can say here is, yes, we have companies using already this the safety checker within the projects. It's hard to say company names, but as said, they use it in their complete development cycle, also for another step of verification and to make sure that the safety architecture as set up is respected and also in place.
Thanks. Is it possible to automatically generate a report using the output in a CI system?
So I think I would need more information about so what we generate, the output comes out to standard console as of the compiler, and so it's in a text format. And then it needs to be parsed from another tool. It needs to be parsed and searched for, let's say, warnings and errors. And then it could be used in a CI system as well, if I understood the question correctly.
All right. How can the safety checker be independent of CPU type if it takes in object files?
Okay.
Such as when the source code is not available, and then the questioner is referred to slide 14 that you showed during the presentation.
Should we go to slide 14? Okay. So, let's wait quickly. So, it does not depend on the object code. To rephrase that, and hopefully I've not said that incorrectly, means the safety checker takes as an input the source files. So if you have the source files, then they take the source files. A third-party vendor has to run the safety checker as well based on the third-party source files. So that's what the third party has to do. And then a so-called VD archive is generated. And this VD archive is not an object file. It depends the access rights, and if the access rights are kept correctly, if there are violations or not. And this one is taken by the safety checker, so it's our own file format. And this VD archive, the third party, hands over to you in parallel to his object code. Okay? So the safety checker does not use any object files. So because of that, he only uses C input files, for example, and then it's independent from the CPU type.
Thank you. Does the safety checker perform an exhaustive combinatorial test of all possible inputs, in order to determine an absolute guarantee that violations cannot happen? And then there's some code has been provided as an example, but it would take too long to read that out to you. I don't know if you can see that on your screen.
I can see it on my screen. Thanks for the question. The safety checker will not do any kind of MCDC coverage tests or branch coverage tests. So the safety checker reads through the C files and checks on the level of wherever you do in your source code a memory access, wherever you have something like, as you said, input 1, 2, 3. Yeah. Is it in the right, let's say, safety class? How are the access rights? So is input, let's say, in the same safety class, and are the access rights correct that you are allowed to write to this variable? Then it's okay. If, let's say, input variable is located in another safety class and the access right is not, it says it's not allowed to write, then it will print an error. So it goes through the code and checks on each memory access, as it knows all the variables, and will print out according to the access rights and safety classes the warnings and errors.
Thank you. Is it necessary to buy a separate license for using Safety Checker?
Yes, it's a separate product within tasking.
All right, thanks. I think you might have referenced this during your slides, which is why the questions come in. What is the VD archive?
Yeah, as said already, it's, let's say, a file that describes if the access rights are kept correctly from third-party software. This, let's say, makes it not necessary of the third party to deliver source code to the company who uses it. Yeah. And so they can keep their IP and just deliver the object code and the VD file.
Got another specific question for you here. What's the difference between partition.saf and linked.cmd interims, I think, of memory mapping? Or interms, I may have misunderstood.
It would be good to know which slide that was.
Yeah.
Okay, well, let's maybe come back to that question. Can you talk about operating systems and what's required to run Safety Checker?
I assume as a host system. So, Joachim, you might want to answer on this one.
Can you just rephrase the question?
Yes. Could you talk about the operating systems required to run Safety Checker, please?
And it's the host operating system. So for the moment, we support Windows machines.
Okay. Have you carried out any analysis on real-world open source projects to understand the ratio of unprovable violation spots?
Let's say we run against a lot of software and own written test software. I would need to go back if we have any specific open source software that we run against.
Okay, the question about partition.saf was also on slide 14. Also referred to something on slide 14.
Can we just switch to slide 4? Okay. Partition SF. So that's the configuration. That's the name of the configuration file. So you can call it anyname.saf. That's what the safety checker takes as an input, where you have defined the access rights. Yeah. And there was a second part of the question.
Yeah, so it was the question was, what's the difference between partition.saf and linked.cmd in terms of memory mapping?
Okay, so it's comparing it to the linker file. So actually there is not a big difference. Basically the the safety configuration, or safety checker configuration, is just a different input, and also points out the access rights and the safety classes, as well as the selection. And actually, only the selection part is really similar to a linker file.
Okay, great. We talked about the analysis on real-world open source projects, to which you answered, and then there's a follow-up question on that. If the checker finds a violation, how do they report it? Where do they report it? And what happens next?
Actually, as we also saw in the example, so it is just small snippets. It points out exactly the location, which file the violation is in, and also the line, and all, actually, as we see it in the example, which function call is causing the access violation.
Yeah, great, thanks. Final question then, how much time penalty does the MPU add?
This is a tough question because that highly depends on the system which is used, the microcontroller. There's different systems, or different technologies available with multiple maps or a single map which needs to be reprogrammed. So the penalty you have if you use an MPU and you have a context which highly depends on the target system. So if it's on an Infineon or NXP micro, and just to name two. But here the operating system. So in the case of EBTrezors, the operating system uses already built-in optimization mechanisms within the microcontrollers, but there is no general number you could name there.
All right, well, that's brought us to the end of the questions and just in time for the end of the hour. So thank you very much to Roman and Joachim for sharing insight with us today. Of course, to Altium and EB for helping to make today's event possible. We will, of course, be sending you an email within the next 24 hours or so, which will have a link to the slides as well as the opportunity to listen on demand to this webinar again. And with that, I'd like to thank everybody who joined us today, of course, everyone who sent in questions, and we'll see you at the next Automotive World webinar. Goodbye.